Hi, I'm Nathan Mikulski, and welcome back to our machine design lectures. Today we'll be covering topic 8, which is fatigue. Let's jump into it. So, everyone kind of has some general idea about fatigue, but for now we're going to focus on fatigue in the sense of continual wear on a piece until failure. So let's look at static versus cyclic failure. Static failure is almost like something sudden that happens, boom, breaks, you're done. Kind of just like when you're bending a pencil, it breaks, you're done. Now, cyclic failure is something that happens repeatedly. So say you have like a piece of metal and you just sit there and start wobbling it. You wobble, 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 eventually it'll start, eventually, boom, it'll break. That's cyclic failure. Now let's look at the major components of fatigue and failure. One of the major components is the magnitude of the loading, and the other is the cycle numbers at the magnitude of the loading. Those two factors together contribute to how the cyclic failure of a machine is, or a component of machinery. Now, how can we look at a strategy to approach fatigue and failure? Well, we can predict the fatigue based off of these two major components, whether it be the magnitude of loading and the number of cycles at the magnitude of the loading. Now, what are the main things we'll be looking at? Let's look at cracks. We're going to be looking at cracks, sorry. Let's start with progression of cracks. Cracks will progress from a micro crack, which is super, super small, and cracks which could stem from impurities in a material, say, and then over time, through the cyclic nature of the repeated stress on the material, it will transition into a micro crack and continually further on to a full crack, and then continually to a failure. Now let's look at some examples of, I skipped one thing. Initiates at material discontinuities, or this progression initiates at material discontinuities where cyclic stress is applied or it's maximally applied. Now we have just a couple examples of it. We have concentrated stress, which kind of just looks like a chunk hit out of it. Sharp corners representing kind of here at these two sharp corners, and then you have internal cracks which will also propagate further. Now there's two main things you got to look at as far as crack goes. You have stress raisers, and there's three different types of stuff that could be stress raisers. The first one is stress concentration factor, which is given by KT, which equals the max stress over the nominal stress, which also equals 1 plus 2C over D. Represented in this figure, C is half the length of the crack from the center of the crack outwards, and D is the vertical half of the crack. And yeah, the second one is stress intensity factor. And there's three progression types of stress intensity factor that you have to look at. The first one is opening crack node, which is due to stress in the field, which is like it's shearing, coming apart, kind of like you would open a book, like that. Sliding node, which is due to in-plane shear stress, so that's when it'd be sliding across each other like this. And the third one is the tearing node, due to out-of-plane shear stress, which is where it'll turn like this. All of those contribute to our stress intensity factor, which is represented by Ki, or K sub I, which equals sigma, so the root pi times A, where sigma is the nominal stress and A is the crack length, shown here. Now, there's a secondary one where you have to worry about a stress intensity factor given by beta, and it's simply the same equation stated before, multiplied by the beta factor, or the stress intensity maturation factor. And the third is fracture toughness, given here as N equals KIC over KI, KI from here. KIC is the critical stress intensity factor, so here at the maximum stress, that's where it's going to be the most critical. Now, the other component of cracks that we need to think about is crack propagation, or how the crack is growing further or faster. And we can look at it in two ways. The first being the cycle life prediction, the first one, given by Paris equations and toughness, which is based on fracture toughness, as given here. So the Paris equation given here is dA over dN equals C times delta Ki to the M, where C and M are both constants given by tables in the book. And we look here at this region. This is kind of the region of like a crack propagation growth. Initially it'll start off super in a non-linear fashion, grow super fast, and all of a sudden it'll start going more in like a linear fashion, then boom, it'll start going straight again. We want to focus on this linear fashion since we can model that. In here, given the crack growth given in this region, the major region we want to focus on that we can actually model with more accuracy is this middle region, this more linear region. We can analyze this way by kind of differentiating our Paris equations. So we arrange it, and it's the integral from 0 to nf dn, so basically nf equals 1 over c, integrating from the initial length of the crack to the final length of the crack of dA over rki, or beta delta sigma root a pi all to the m. This is just a base equation of this rewritten out to show where this came from. Now, the other way we can look at our crack propagation is based off of our prediction 2 given by SN curves. Here is like a quick model of an SN curve given all these cyclic tests. That's what all these dots represent. All these dots represent another test point, another data point collected in a study. Now, there's multiple different regions here and multiple different things you can come to determine, and multiple things that you can also determine from other properties in here. Here note that the ultimate tensile strength, or the ultimate strength of the material is kind of the starting point that you want to look at for 0 cycles, n representing the number of cycles. So at no cycles, it would break at its ultimate strength. And here we see that as the cycles continue and go off to like an infinite amount of cycles, you reach a point called our endurance limit, would get represented by SE. And using this, we can determine where stuff would have low cycles or high cycles, or a finite life or an infinite life. Those two, a finite life and infinite life, being the more prominent of the two. We'll come back to this in a second. Now, let's look at the problems with the SN curves. Like I just said, all of these dots represent data points. And someone had to take data points, someone had to conduct a test, someone had to find it that way. Well, that takes a long time because it's done experimentally. So instead of looking at this SN curve and taking all these data, we'll look at an idealized SN curve. An idealized SN curve, we definitely want to focus in on this middle region represented by the black line. And to define a line, you only need 2 points. And here we're going to look at 2 points at n equals 10 to the 6th cycles, or 1,000,000 cycles, or 10 to the 3rd cycles, right? And we're going to set our 10 to the 6th equal to our endurance limit, and our 10 to the 6th is equal to a function of our ultimate strength. And here we're going to use this equation to model our line. So the SF equals a n to the b. A is represented by SUT squared, or the ultimate strength squared, over the endurance limit. And B is represented by the negative 1/3 log of the FSUT over the endurance limit. Here's just a quick redraw of this line here, representing what we were looking at to determine our idealized SN curve, and what we will use to define our fine ultimate strength, endurance limits. Now, endurance limit is also kind of a touchy thing. It is determined by, we can look at it as like an endurance limit, and we can look at specimens. But if we're looking at specimens, we have to account for a bunch of other factors or modules. So here we have our equation for our endurance limit. SE prime, or the endurance limit prime, is the endurance limit of our specimen, and we have to multiply that by a bunch of different modules, varying from temperature to surface finish to all these other types of factors that would go in there. Here we also have a base rough layout of what our SE prime could be, just off of statistical data analyzed. So here we see that for our ultimate strength of less than 200 kpsi, excuse me, our ultimate strength of less than 200 kpsi, or 1400 megapascals, we're going to use 0.5 times the ultimate strength as our SE prime. And if it's over 200 kpsi, we'll use 100 kpsi for SE prime, or 700 megapascals if it's over 1400 megapascals. So basically you kind of have two cases here. Now let's move on to fatigue stress and concentration factor. Our concentration factor is given here. Our KT is sigma max over sigma naught. Those are something that will be applied into your equations as well. And I also want to lightly touch on stress concentration and notch sensitivity. Our notch sensitivity Q is given by Kf minus 1 over Kt minus 1, where our Kf is our dynamic factor of fatigue stress, or the dynamic concentration factor, and our Kt is our static concentration factor. Now, note that our dynamic is less sensitive because it doesn't notice sudden spikes in increases in stress, like say a static would. If a static component had a sudden increase in sensitivity or pressure or something, it would feel that really fast, like something that's statically ding, boom, breaking. If it's sudden, you got it like that. Now let's also look at one more component. We can look at non-completely reversed systems, which is traditionally our systems when applied to stress would look like a sine wave per se, hovering around like the x-axis line, say, or the timeline. Here we can see that, and then that would be completely reversed, and because it's just hovering around the same line. Here it's not completely reversed because we are offset by a certain amount, and it will contribute different ways to our fatigue. And one more thing we should look at is a modified Goodman line. Here we see that our endurance limit and our ultimate strength are compared to our sigma m and our sigma a. And we can use this to find our n, given by this equation here, which is sigma a over an endurance limit plus sigma m over our ultimate strength. And we find that if that ratio is less than 1, it will be below this Goodman line, the modified Goodman line, and it will have infinite life. And if it is greater than 1, it will be out in this region and it will have finite life. I hope this helped you to understand the topic of fatigue a little bit more. See you next time.